we've seen that we can use Green's theorem to rewrite circulation integrals as integrals of curl over an interior region, or line integrals involving flux, or flux line integrals, rewrite them as a double integral for involving divergence. And that is an important, useful way of using Green's theorem. But Green's theorem actually, or that ability involving Green's theorem, lets us do a number of other things as well. So there are other ways we can use Green's theorem that turn out to be very useful. So one involves this problem that we ran into when we talked about conservative vector fields. So we hoped that if we had a vector field that satisfied this equation, partial n partial x equals partial m partial y, we hoped that this would be enough to detect a conservative vector field. But in fact, it's not. We had this example. So we worked out this example. It does satisfy this equation, but this vector field is not conservative because there are line integrals around closed loops that aren't zero for this vector field, right? We showed that if a vector field is conservative, so if it is the gradient of something, then line integrals are path independent, and a result of this was that line integrals for this vector field around closed loops, closed curves, always equal 0. Okay, but for this vector field, if you just integrate around, say, a unit circle, you don't get 0. So this vector field isn't conservative, even though it satisfies this equation. Right, so what gives? Oh, by the way, vector fields that satisfy this equation are called exact sometimes. So this vector field is exact, but it's not conservative. Okay, well, the problem with this vector field is that there's a hole in the domain right at the origin, right? And this loop that we're integrating around to get a non-zero value goes around that loop. So what if we didn't allow that to happen? So what if we require that the domain of our vector field be simply connected? Simply connected just means that the domain has no holes. So if we insist that the domain be simply connected, we're disallowing this kind of hole. So what I'm saying is, let's suppose that we have a vector field f, which we'll call m comma n. Suppose f is exact, which remember means that partial m partial x equals partial m partial y. So f is exact on a simply connected domain. Okay, well, what does this have to do with Green's theorem? If you look at this equation for exactness, we could rearrange this. We could rewrite this as partial n partial x minus partial m partial y equals 0. In other words, curl of f equals 0. Okay, so by assuming that this vector field is exact, we're really assuming that its curl is 0. So now we have a simply connected domain and a vector field whose curl is 0. So let's think about integrals. So what about the integral over a closed curve? So if we do a line integral over a closed simple smooth curve, or piecewise smooth even, of f dot dr, well, the closed simple smooth curve, these are exactly the curves that are boundaries for regions. So Green's theorem says that we can switch to a region, a double integral of the curl of f over the region dA, over the region that is the interior of our curve C. And this we couldn't do if there were a hole in the domain, right? So our curve is some closed simple curve like this. If there were a hole in the domain, we wouldn't necessarily be able to do a double integral over this region. But by assuming our domain is simply connected, we can know for sure that there aren't any holes inside of this interior region, and so this double integral is something that exists. So since this double integral exists, we can actually think about what value it should have, and well, by assuming that the vector field is conservative, we've guaranteed that the curl of f is actually 0, and so this double integral is going to be 0. So that means that the line integral, the line integral around any closed curve is equal to 0. So why does that tell us that? Line integrals have to be path independent, right? So if we have a line integral over this curve C1, f dot dr, what if we had a different path with the same endpoints, right? Like this, maybe. Right? That would be the integral of C1 dot dr. Right? Why? We're hoping that these two are equal because remember, if line integrals for f are path independent, we have already proved that that implies that f is conservative. Okay. So we now are in a position to know that if we have an exact vector field on a simply connected domain, then integrals around closed simple curves are 0. So why does that mean all line integrals are path independent? Well, if we have two paths from point A to point B, like this, right, we can turn C2 around. Right? If we turn C2 around and go around this entire loop, that gives us the line integral over C1 plus minus the line integral over C2, because we're going across C2 backwards when we go around this loop. So f dot dr. But right, this is the line integral of C1 and then C2, but going backwards. So this minus sign just means we're going backwards. F dot dr. But now we're going around a closed loop, and we just saw that the integral around closed loops is 0. But right, now that we know that this difference is equal to 0, now we can rearrange this. We can take our C2 integral, move it to the other side, and it shows that these two things are equal. So, so now we have a condition that tells us when, or we've proved the condition that tells us when vector fields are guaranteed to be conservative. Okay, so what we've shown is that if f is exact on a simply connected domain, right, we proved that line integrals over closed loops are equal to 0. That implies that all line integrals are path independent, and then we already knew that this implies that f is conservative. In other words, f is the gradient of some function, little f, some potential function. All right, so that's one use that we can use Green's theorem for. It lets us sort of fill in this gap about this, this condition for conservative vector fields. All right, here's another way we can use Green's theorem. So let's show that this this spin field does work around every simple closed smooth curve. Okay, so work is just a circulation integral essentially. So work is an integral around a curve of f dot dr. But a simple closed smooth curve is the boundary for some region. But then we can use Green's theorem, right? This vector field is defined everywhere, so it's safe to switch to a double integral over the region R of the curl of f dA. So what is the curl of f? If we work out the curl of f, so partial n partial x is -1 minus partial m partial y, that's 1. So we get the double integral of -2 over this region, but that's just going to be -2 times the area of R, right? So, right, this area can't be 0 because part of being a simple curve, that means that it doesn't self-intersect, right? And if your curve does, right, the only way for this area to be 0 would be if you went out and then back along the exact same path. But that can't happen because then you'd be intersecting yourself a lot. So this can't happen, and that means that our curve has to enclose some area, and so this area is definitely not equal to 0. So that shows that this spin field does work around every simple closed curve. There's no way to choose a path so that this field does no work. A closed path, simple closed path. All right, final way to use Green's theorem is this sort of thing. So this partial differential equation is called Laplace's equation, and the reason to study Laplace's equation is because it shows up in all sorts of physics contexts. So I won't show you any physics contexts where it shows up, but just take my word for it that it shows up in all kinds of funny places. So so a function satisfies this equation if, when you plug the function in here, these second-order partial derivatives add up to 0. So there's supposed to be a t in here. So let's prove that if our function satisfies this differential equation, then, or this partial differential equation, then this line integral is equal to 0. All right. So something you might notice about this line integral is if we rearrange things, we can write this as a line integral of a vector field, right? Oh, well, so we're going to prove that this is 0 for all closed curves for which Green's theorem applies. So, of course, at some point we're going to use Green's theorem. So let's try to rewrite this as a line integral of a vector field. So this is going to be the integral over C of, let's see, right? We want this to be as some vector field dotted with essentially dx comma dy. So, right, this is really shorthand for x prime comma y prime dt. Okay, so we need our dx to go with partial f partial y, so that's here, comma, and then we need our dy to be with partial f partial x, so that's going to be here, partial f partial x. But to get this minus sign, right, we have to stick a minus sign here. Okay, so we get this line integral. So this is the line integral over the curve of partial f partial x, partial y, sorry, minus partial f partial x dot dr. But now we can use Green's theorem because we're assuming that C is a curve that where you can use Green's theorem. So that means that this curve is the boundary of some region, and we can do a double integral over the region of the curl of this vector field. So what is the curl of this vector field? Right, dA. So what is the curl of this vector field? Well, so the curl of the vector field is it is the derivative of this with respect to x, so minus partial, well, this already has a derivative with respect to x, so if we have another derivative with respect to x, we get the second order derivative with respect to x like this, partial squared f partial x squared, okay, minus, and then we need the derivative of m with respect to y, so that's going to be the second partial of f with respect to y. So partial squared f partial y squared. Okay, well look, now we have these second order partials. This is the negative of the double integral of partial squared f partial x squared plus partial squared f partial y squared dA. But this, right, we assumed that our function was a solution to Laplace equation, which means that this particular sum happens to be 0. So we're integrating 0, and so this whole thing is 0. Okay. In fact, this fact that being a solution to Laplace's equation implies that this line integral is 0, this does actually go backwards, which amounts to using Green's theorem backwards.